Some of these energy systems, I think it's just really useful for athletes to know the basics behind how we make energy because we use so much energy, so we should know a bit about it. So first of all, let's define energy. All it is the ability to do work, move things, heat things, make things happen. It's found in chemical bonds in our bodies, particularly phosphate bonds. So, overview, you have ATP. This is just stored energy in your body. This is only going to last you about 5 seconds, and it's going to yield us the most power output. Phosphocreatine, CP, creatine phosphate, whatever you want to call it. This is going to be super high energy as well. It's going to last us about 10 seconds. This graph says more. I would say 10 to 15 seconds, as far as I know. Anaerobic glycolysis. This is like where things get shitty, right? This is your 400-meter all-out pace. This is gonna last you up to 80 seconds if you're normal, 2.5 minutes if you're super fit. Yeah, we'll discuss that a little bit later, but this is where things start to hurt, right? This is where CrossFit lives a lot of the time. Aerobic glycolysis. This is a really good system, guys. This is going to be yielding you tons of ATP. It's super efficient. It's not as fast as like phosphocreatine or stored ATP. That's why its power output must be lower. But you can pretty much go with aerobic glycolysis for several hours and just be chilling and fine. This is where your Ironman triathlon lasts, or where it stays. Your aerobic lipolysis. This is where we start using fat exclusively. If you get into this, you are fasted, and if you don't intend to be there, you're in a bit of trouble. It's okay to go into it, of course, but this is a starvation mode, and that's like after 5 hours. So if you're exclusively in lipolysis, call someone. You need help. Okay, first one we've got creatine phosphate. This one's simple. This is like the most archaic and ancient way to make energy. You've got creatine and you've got a phosphate, and they're bound to each other. And you break that bond, and then you have energy. It is so simple, and that's pretty much the extent of it. You also have your stored adenosine triphosphate, and this is an ATP, guys. So you've got the A, adenosine, and then you have a P. All of these bonds have energy. Usually we're only going to break this first bond because you want to keep ADP around. I'll explain that later. But just know that we're breaking this first they're breaking this first phosphate off, and that's gonna yield us a bunch of energy. So cellular respiration. Don't get intimidated. This is not that complicated, I promise. First, let's discuss anaerobic glycolysis. So you've got a glucose, and we're going to lyse it. So glycolysis, we're going to cut the glucose. That's going to yield us 2 ATP regardless of if there's oxygen or no oxygen. But if there's no oxygen, we're going to go and make some lactic acid. We're not plants, so we don't make alcohol, but plants do make alcohol. That's not really important to us because we're not plants, like I said. So if we want to get nitty gritty with it a bit, you're going to start with the glucose, and then an enzyme called phosphofructokinase is going to kind of slice that glucose in half, and that's going to yield you that ATP, and it's going to make it into a pyruvate. A pyruvate is essentially half of a glucose. So it's C3H6O3. When you don't have any oxygen available, you're going to get another enzyme called lactate dehydrogenase, and that's going to turn that pyruvate into lactic acid. Lactic acid has energy. It's useful for us, so we can use it in our aerobic system later. But the negative to lactic acid is that it's going to inhibit enzymes because it's decreasing the pH of your blood, aka making your blood more acidic. In muscle phys, we call that OBLA, onset blood lactate accumulation. So when you get to the point where you have so much lactate that you're not efficiently able to make energy because your blood is so acidic, we call that onset blood lactate accumulation. And at that point, you need to slow down. You won't be able to continue exercising that fast. But yeah, so we can convert that lactic acid back to pyruvate and use it for the citric acid cycle, or this Krebs cycle right here. We don't need to go into the details of how you make pyruvate back from lactic acid. That's just too complicated, and we're not physiologists or biochemists, so that's okay. A little more detailed here, image of the citric acid cycle or the Krebs cycle. It has so many names. Don't worry about all the names, but basically we're going to shuttle pyruvate right through here, and that's going to yield us 1 NADH, 2 NADH, 3 ADH, NADH. Additionally, it's going to give us an FADH2 and a GTP, okay? So 3 NADH per cycle, 1 FADH2, and a GTP, which essentially is an ATP for our purposes, right? It's just an energy-carrying phosphate-bound molecule, right? You're actually going to do this twice in reality, so you're going to end up with 6 NADH, 2 FADH2, and 2 of those GTPs, right? So what does that let us know about aerobic glycolysis or the Krebs cycle? Well, we're not actually getting that much energy from the Krebs cycle. It's only giving us 2 total ATP. That's just as efficient as anaerobic. Why would we bother using this? Well, we use this because of the NADHs and the FADHs. These become important in the next thing that I'm about to show you. But essentially, these H's, these hydrogen ions, these are our money makers for ATP. So let's go look at the electron transport chain. Okay. Again, don't get intimidated. We're just looking at a mitochondrial membrane. So this is the inside. This is the mitochondrial matrix. So this is on the innermost side of the mitochondria, right there. So this is the inside of the cell. This is the inside of the mitochondria. This is between those two areas, if that matters to you. It should. Anyway, we're taking those NADHs and FADH2s that we got from here, right? We got those here. We're bringing them here. We have these protein complexes, but essentially what's going to happen is NADH is going to come up to here, be like, cool, take my hydrogen, please. And it's going to shuttle it into this intermembrane space. FADH is going to do the same. It's going to shuttle its hydrogens into this intermembrane space. And this is happening extremely fast. So you're putting a ton of hydrogen ions into this intermembrane space. At the same time, you're taking those hydrogen ions out of the mitochondrial matrix. So what you're doing is you're creating a gradient. So you have lots of hydrogen in here, like very little hydrogen out here. And what does that cause hydrogen to do? Well, it wants to go where there's not a lot of hydrogens around it. It wants to go to an area of lesser concentration, if you want to get all chemical about it. Those hydrogens are going to rush through ATP synthase, and that's going to give you ATP. That's the simple answer, but ATP synthase is one of the coolest things that I've ever seen in my life. I think it's really neat. I want to show it to you. So this is an ATP synthase schematic. This isn't actually what it looks like, of course. Those colors aren't found in nature. Anyway, you're going to have hydrogens rushing through this tube, and what those are going to do is it's going to cause this head to spin. So inside of this head, think of it like a middle school dance, and you have your ADP on the left and you have your phosphates on the right, and they won't interact with each other because they're just scared to do so. Well, when hydrogen comes in here and spins that up, it forces them to collide, and that actually causes the synthesis or the creation of ATP. So you're just smashing phosphate to ADP and forcing them to make ATP. Pretty cool how that works. But yeah, so that can only happen if these hydrogens are rushing through and causing that thing to spin. Really neat. Here's another schematic. This is from a gram-negative bacteria. But anyway, it just goes to show you that bacteria are doing the same thing. So hydrogen is rushing through here, causing this head to spin and smashing together ATP and ADP and phosphate to make ATP. So pretty cool how that works. That was just a quick and dirty way to think about all of the energy systems. We didn't go through the complicated enzymes and stuff because that stuff's really not that important. At the end of the day, all you need to know is that your most efficient systems are also less powerful, and your more powerful systems are less efficient. Um, and of course, this isn't exactly how it works, because in reality, all of these energy systems are working in concert slightly. Like aerobic glycolysis never shuts off. And that's actually really, really good for us, because that means our anaerobic glycolysis can get buffered, or rather, the lactic acid can get buffered by the aerobic system no matter what. Also, guys, a good reason to warm up. If you can get your aerobic system working a bit before even you hit an anaerobic workout, well, then now you're in that more efficient energy system that's just a little less powerful, and you're going to be able to, again, buffer that lactate a lot better. So I hope that helps. Let me know what questions you have. Thanks. Bye.